in all those situations. So I'm going to digress for a second from the actual emulator and talk about the supporting modules. And these are other Python modules that PyEmu will rely on to provide that flexibility. And I think these modules are, exemplify the whole Python reversing community because they're very good. They do their job well, and I rely on them, and hopefully at some point someone may rely on PyEmu and things of that nature. So we're just going to talk about a couple of those supporting modules. PyDasm, which if I didn't have that, I would never have been able to write the emulator. It was created by Arrow, who's right over there, works for Sabre. It's a bunch of good guys, but it wraps libdasm, created by JT, who it's actually wrote it as a C library. Provides a raw byte-driven disassembler library, and this is the piece that I enjoyed the most because having a disassembler that will just take raw bytes, via Python or however you instantiate it and whatnot, just allows so much flexibility. You can give it a chunk of bytes, return instruction, you're good to go. And currently, IA32 specific. And as I put down there, PyDasm is the only thing you can't have. You can do everything else. You can use the emulator without these other modules that I have here, but you have to have PyDasm. That's because I didn't want to write a disassembler. Just like I hope someone doesn't write a Python emulator. And a quick example from Arrow himself. This is just how an instruction gets decoded, and you'll get that instruction. I thought I had the output in here, but basically this was just print out the mnemonic, I believe. Next, IDA Python. I'm sure if you code Python and you use IDA, it's just natural to use IDA Python as well, I guess. Created by Gersley, I believe is how you would say it, from F-Secure. Allows Python scripts to be executed in IDA Pro, provides access to IDA's IDC and SDK functions, and also provides higher level functions that are easy to use and give you a little more flexibility inside of IDA Python. And it's a must-have for anybody that's scripting inside of IDA Pro. I use it every day. It's pretty nice. But it allows PyEmu to work in IDA without much worry. And if you look at this, just a quick example of how IDA Python is used. Fetches code refs. It'll give you all the functions in the binary. So next up, PyDebug and PyMA, created by Pedro Amini. It's over there, OpenRCE. If you haven't been to OpenRCE, you should go. It's a pretty good website. There's a lot of communities, blogs, and everything on it. But PyDebug, at least, is a Python wrapper for the Win32 debugging API. Allows you to fully script, a live debugging session. You can, of course, attach, load, set breakpoints, query memory, create all these handlers and whatnot. And like the others, allows PyEmu to be used during live analysis. So we're kind of working hand in hand with these modules to provide all these different environments. But if you work on Win32 platform, you should definitely check out PyDebug. It's extremely useful. Here's an example. I know these are hard to read up here, but it's PowerPoint. So this is just the basic. It'll set a callback to do all the breakpoints, attach to the process, and then run it. And this is actually all you need to attach to a process and execute it, and catch breakpoints. PE file, again, created by Arrow. Just the Python madman over there. What this is a Python library for parsing PE executables. Allows scriptable access to all parts of the PE, headers, optional headers, directories like your import, your export, all those things. It's so useful for looking at different, maybe packed executables and things of that nature. And again, we rely on it in PyEmu to do the PE file command line stuff. So thanks, Arrow. This one will basically print out all the imports. So right now we'll go back towards the emulator and talk about using it. What we'll do is cover instantiating it, all the exposed APIs, things of that nature, the handlers and whatnot, everything I provide for people to control it and everything like that. So, one of the focuses was it should be natural and flexible. I wanted people to use it and to extend it and, change it for their purposes. Tries to provide a logical layer to achieve RE task. We talked about a couple of the tasks that we want to achieve, and hopefully, this would be a logical way to achieve them. Provides methods for instantiating, setting variables, reading, writing memory, logging, of course, executing, and things like that. So, instantiation. 3 environments are provided. We've talked about those extensively. The user must instantiate or create the proper object that they'll be using in their environment. All 3 classes inherit from the base PyEmu, so when you're creating a new environment, you don't actually have to use or extend a lot of these different methods. You can just, access them through your class. And it's easily expandable, often taking a couple of minutes. So, just an example, if we're working in IDA, the first thing in the script would instantiate the IDA PyEmu, and this is what it takes to actually create your emulator. It is just a base skeleton of your emulator. From there, you can, use it as you would. And I go through the setup. The setup is after you have an emulator object. These are things that you need to do in certain environments or things that you want to do in certain environments. What this includes is mapping the code and data sections. You obviously need to be able to fetch instructions, so you need to let the memory manager know that you have certain data in certain places. Setting up EIP to a proper location. For instance, in the live debugging versions in the PE file, you can specify these on the command line, and it will tell the emulator which place to start executing code in. And what you can do is, if you wanted to just say you did these things all the time, or you had you didn't want to just use them all, use the same canned phrases in each script you write, you could just take them and put them in your environment class if you wanted to. So you'll see right here, this is IDA PyEmu, and this is basically how you map the sections. So you'll see emu.setMemory with the original byte, which is reading from the IDB. So I don't know how fun code is to read on a big screen, but you'll see at the bottom, emu.setRegister. We'll set our EIP to the current screen EA, and if you don't know, screen EA is basically where your cursor is in the IDB. So next we have handlers. Handlers allow us control over important situations. The last one says the bread and butter of PyEmu. The handlers are there to trigger and provide control back to the user or the user's script, depending on certain situations that happen inside of the emulation. There's tons of them in here, and it contains handlers for most aspects. So what you do is you'll instantiate, set a handler, and when that situation happens inside of the emulator, it'll call into your code. So we'll go over all the handlers because I think they're pretty important, at least for, some pretty good scripts you may be writing. Register handler, and all these are self-explanatory. So return execution when a specific register is touched. So if a register gets updated, if a register gets read, anytime that register is accessed, you'll get your handler called. So when your handler gets called, it'll pass the register, the value, and the type of handler, for instance, read or write. So if I wanted to say, give me, or I want to log every time EAX is updated, or ECX, then you would set an ECX register handler, and when that would happen in the emulator, it would call back into you. The handlers also have control as opposed to which way you return. If you return from your handler with false or none, it will usually, in most cases, for instance, in the mnemonic handlers and stuff, it'll stop execution of that particular block. So, for instance, if you had a write handler for memory and it called into you and you returned false, it wouldn't write that piece of memory. So there's a little bit of control in the way you return from the handlers. And you'll see this is how those get set up. It's real easy. You'll take the emu object that you instantiated and you just set register handler. And as you can see, and I've said, they take a function pointer. So just any function you define, you can pass in. Libraries, returns execution when a specific library is called, allows you to catch external or imports that may be happening in the binary, or calls outside of the loaded code base and things of that nature. Many standard library calls are actually provided to hook in the emulator. If a call is not emulated, Python tries to load the library and call the export and then emulate through that. So you can see set library handler. Malloc would actually trigger anytime malloc is called. Exception handler returns execution when a specific exception occurs. The function expects the Intel-defined exception code. GP is a general protection fault. Things like an access violation and a memory fetch will call into your handler. I have two different ways, and I didn't really put that in the slides, for handling unknown memory request. You can either execute in fault mode or non-fault mode. And what that means is in fault mode, if you try and grab memory that is not actually in the cache and it needs to be requested, it'll create a access violation like a normal a normal program would, since it can't, since it doesn't already have it, hasn't been allocated, it's going to throw a violation. However, you can operate in non-fault mode, and what that'll do is it'll call back into the memory handler that you're using, for instance, the IDA PyMemory handler, and call its allocation routine. So, for instance, in the IDA one, if I execute in non-fault mode and I'm requesting a page of memory that doesn't exist, it calls into my IDA PyMemory class, and I basically return a string of A's at page size. So each time IDA hits a memory request, it won't violate, it'll continue, but it'll get a block of A's. And that can be useful in different situations. The more live analysis ways, if you use something like that in the PyDebug PyEmu memory class, it'll actually request memory from the parent process, from the real process. So here's mnemonics. Like all the others, they're pretty self-explanatory. Return execution when a specific mnemonic is encountered. Allows the user to hook every interesting mnemonic. Can be useful for enumerating certain branches in code. I have an example later, but you could say, give me control every time compare is hit. Give me control every time a move happens. Give me control every time a call, a jump, things of that nature happen. So it's pretty useful for gathering that kind of information. And like I said, if you return false from these functions,
what happens if, by example, you see a multiply or multi or instructions that have multiple prefixes before?
I handle all those.
But, if I set an handler on revenue or law.
So you would have to specify that as a string, as a multi-byte string, right? So, you would put it in there as you would see it in normal disassembly, right? So if you do provide any of the, rep instructions or things of that nature, you'd have to be just a, rep, move, and things of those, so. And as far as, move S, move D, you would put move D, move S, things like that. So however it's defined in the Intel manual, it would be in there. And then an opcode, we further take that to a more granular level, and you can do just specific opcodes. You could do only, an 8-bit immediate version of move or, things like that, and you would specify the actual hex opcode for that. And for multi-byte opcodes, you would put both of the bytes in there. So